Welcome to this second talk of our 3 talks today that we're going to have on use of generating functions methods in symplectic topology. So this talk is given by Allais from ENS Lyon, and he will speak about periodic point of Hamiltonian diffeomorphisms of projective space and generating functions. Please go ahead.
Okay, thank you very much for the invitation. So the topic of my talk would be the study of periodic points of Hamiltonian diffeomorphism, exclusively on the space, on the complex projective spaces by the use of generating functions. So I will not prove or give hints to new theorem, but my goal is to give you other way to prove a recent result of symplectic dynamics on CPD using only a generating function and most theory. So as I've just said, I will restrict myself to CPD with the usual symplectic form given by the Fubini 2D metric. And first of all, let me recall you the famous Fortune-Weinstein theorem, which states that every Hamiltonian diffeomorphism of CPD has at least D plus one fixed points. So, in other words, the Arnold conjecture is true. It was proved before Floer proof. So it's so the Arnold conjecture is true on CPD for the dimension of the total homology of CPD is D plus 1. Okay, and well, my object of interest here will be periodic points, which are defined to be the fixed points of the union of fixed point of the iterates of Hamiltonian phi. And well, contrary to the aspherical case, it is possible to have on CPD Hamiltonian diffeomorphism with only finitely many periodic points. A very simple example is given by what we can call irrational rotation of CPD. So take A0, AD real numbers which are which are Q independent, so rationally independent, and consider this map. Well, it's easy to see that this is a Hamiltonian diffeomorphism. It's generated by a quadratic one, and it only has D plus 1 periodic points, which are the the projection of the canonical base of C D plus 1. So those are the only periodic points of this Hamiltonian, and there are D plus 1. Moreover, there also are the fixed points of phi. So we are in a special case where the periodic points of phi are exactly the fixed point of phi, and there are minimal in number according to Fortune-Weinstein theorem. So we also see that this is a sharp theorem, of course. Okay, and this suggests this definition. A pseudo-rotation of CPD is a Hamiltonian diffeomorphism which satisfies this equality. So the set of periodic points is exactly the set of fixed points, and it is minimal. So D plus 1. I restrict my talk to CPD, so it's D plus 1 that should be here. A long-standing conjecture about periodic points of Hamiltonian diffeomorphism is the Hofer-Zehnder conjecture that a Hamiltonian diffeomorphism of CPD is either a pseudo-rotation or has infinitely many periodic points. So either you have D plus 1 periodic points, in this case, those are your fixed points, or you have infinitely many periodic points. So it's still open today, and now I will discuss theorems, results that discuss this conjecture. We will see some results that can our goal is to see how close it could be true. So this conjecture, yes, it was suggested by a theorem of Frank's two years before. It was conjectured by Hofer-Zehnder because Frank's proved that this is true on the sphere, on the two sphere, which is the case D equal 1 for us. Okay, so a theorem which tells us about what kind of condition can imply the existence of an infinitely many periodic points is given by the theorem of Ginzburg-Gürel in 2014, that Hamiltonian diffeomorphism of CPD that possess one hyperbolic periodic points, at least one, has infinitely many periodic points. So, an obvious converse is that a pseudo-rotation cannot have hyperbolic points, and in fact, the proof of this theorem, the proof of Ginzburg-Gürel, tells us a bit more. And in fact, it was pointed out by Ginzburg-Gürel a few years later. One can say that fixed points of a pseudo-rotation of CPD are not isolated as invariant sets. What does it mean? It means that if X, so say X is one of the fixed points of your pseudo-rotation, then it's not isolated, means that for all U neighborhood of X, you can find, so here, U, there exists some point which is not X inside U, such that the image under, the dynamic of Y is contained inside U, past and future of this dynamics. So for all K in Z, this is important. Otherwise, hyperbolic points would be also isolated. Phi K of Y is inside U. So this is a special property that satisfied every fixed point of a pseudo-rotation. Another theorem about this conjecture of Hofer-Zehnder is the famous theorem of Shelukhin. This recent result almost proved the conjecture. In fact, it proved the conjecture in the non-degenerate case. So if phi is well, if the graph of phi is transverse to the diagonal, the conjecture is true. And in fact, it proved much more than that. It proved the conjecture with another, well, a homology version of the conjecture, where you replace the usual count of fixed points by a count of fixed points with multiplicity, the dimension of the local homology. Well, it's a bit technical, but well, in general, there is no clear relation between these two ways to count the fixed points. But in the non-degenerate case, those are the same. Okay, so these three last theorems, so these three recent theorems are in fact proved in a much large class of symplectic manifold, monotone symplectic manifold. And well, it's not all monotone symplectic manifold, but there are properties, there are specific constraints on the quantum homology of the space on which those theorem applies. For instance, for the theorem of Shelukhin here, the quantum homology of M must be semi-simple. For this theorem, there are other conditions. There are numerous conditions. One is that the Q operator must be must decompose as the product of two classes which lies inside the usual homology of M. Well, and other, well, there are other conditions. So there are constraints on the manifolds that are that has to, well, that are linked to J-holomorphic curves. And the goal today of my speech is to prove this theorem in the special case of CPD without appealing to J-holomorphic curve theory. But well, in some sense, the J-holomorphic curves are still there because in the case of CPD, with the usual complex structure, it's only projective lines, so it will be still there in the proof in some sense. So no J-holomorphic curve theory, but it will be based on generating functions, and especially based on the works of Givental and Théret, who both prove with their use of generating function, both prove the Fortune-Weinstein theorem, and some some extensions of that. So it will mainly, I will mainly talk about their theory. So in order to fix notation and convention, let me recall how we define the action of a fixed point of phi, which is a Hamiltonian diffeomorphism of CPD. So we will fix once for all, this is important, we fix once for all a Hamiltonian H, generating phi as the time one map of the Hamiltonian flow. Well, we can say that it is a periodic if you want. Maybe here, this is S1. So, and given a fixed point, you can define the action of it as the action of the Hamiltonian orbit phi t of x. So you know that because CPD is not aspherical, you must you must choose a specific capping, or X bar, so which is a map, well, a mapping of the disk with well, the boundary of the disk equal to phi t of x, and up to, well, once you have this choice, you can define this real number with the usual formula of the action, well, with the small exception that I have a reparametrization there, a scaling there, so that it will be so that the action of the fixed point will be defined up to integer and not up to pi z. So this formula makes total sense for x bar, and if you want to forget about the capping, you must see this number as up to integer, as a number in R over Z. For if you take a recapping by a sphere, so the pi 2 of CPD is generated by CP1, by a projective line. So if you attach a CP1, you will have the action with -1. Okay, because the area of CP1 is pi. Well, everything is certainly well known for everyone here. So now that we have fixed our convention and we have fixed our Hamiltonian, because if you take a constant, it will give another action. So we have fixed this Hamiltonian. We will now lift our problem to CD plus 1. So this is a very standard procedure. It was already done by Fortune Weinstein in their proof, their original proof of the Arnold conjecture. So given our fixed Hamiltonian small ht, we define capital HT to be the two homogeneous and S1 invariant Hamiltonian map that is the same as, well, that project to small ht when restricted to the Euclidean sphere. So here S1 acts on CD plus 1 by well, it's act by multiplication by a complex number of modulus 1. Okay, so saying that this is two homogeneous and S1 invariants can be write down as satisfying this equation for all z in CD plus 1 and all lambda complex. So you are, in some sense, two homogeneous in a complex sense. Okay, so this Hamiltonian generates a Hamiltonian diffeomorphism capital phi, which will satisfy this this equation, which can be seen as some kind of C equivariance. So it is a true genuine Hamiltonian diffeomorphism on CD plus 1 minus 0, and the following diagram commutes. So it's really a lift of our initial phi, and well, we can extend it to homeomorphism of CD plus 1 by homeomorphism fixing 0. So this homeomorphism, I will say, is the C equivariant Hamiltonian diffeomorphism, the C equivariant Hamiltonian lift of small phi. So it depends on the choice of H, but we have fixed it once for all in order to talk about the action. So now, because there are complex numbers there at stake, fixed point of our small phi will not lift into a fixed point of capital phi. In general, there will be a phase, some phase here. Well, the module is the modulus is stable. Well, is fixed. Well, because of the two homogeneity, but in general, there will be a phase, and in fact, this is an important remark made by Théret. In fact, this T there, so this T, which is it can be seen as a real number up to integers, is the action of the associated fixed point of small phi. So this is very, very striking, and hence C lines of fixed points of exponential minus 2ipt times capital phi are in 1-to-1 correspondence with fixed points of phi with action T, with the same T here and there. Okay, so this is the fundamental remark. And now I want to, well, my goal here, in order to find back this numerous theorem I've told you about, is to construct some kind of Floer homology without Floer theory, but only appealing to usual mass theory of a function. And so now I will need a variational principle with real valued function on a finite dimensional manifold. And here comes the generating function. So generating functions have a long history going back to Jacobi and then Poincaré to this in order to study a small deformation of the phase space. And well, the modern theory that I used, well, the theory used in order to study Hamiltonian diffeomorphism, which are a bit further than to identity, was due to numerous work, among those the work of Hermander, Sikorav, Viterbo, Chekhanov, of course Givental and Théret, Chaperon, of course, and many others. Here, the point of view I will give you is very close to the point of view of Chaperon. So it's a special instance of generating function of Lagrangian isotopic to the zero section. In fact, this is the case when you take the graph of the Hamiltonian diffeomorphism as Lagrangian in the product CD times CD, CD plus 1 times CD plus 1. So this theory is well behaved for Hamiltonian of CD plus 1. So we will apply it to our Hamiltonian, C equivalent Hamiltonian. But let us start with some Hamiltonian, capital phi, which is a finite product of small Hamiltonians. That is Hamiltonian diffeomorphisms that are C1 close to identity. So there is an explicit number for that. So when such a decomposition, such finite decomposition exists, you can find, you can define a function with an explicit formula, although I will not write it down here, which take as many coordinates as the number of small Hamiltonians. So it is a n-tuple Z1, Zn of points of CD plus 1. And let me give you a geometric insight on the variational principle. It works a bit like the finite dimensional reduction of the energy of closed geodesics, for instance, if you know a bit this theory. So given n-tuple Z1, D2, D3, Zn, I want to understand a bit what should be the gradient, the differential of f sigma. So let us write the image of the Zj under the sigma j, the associated sigma j. So in general, we will have something like that. With no real relationship between the image Zj, sigma j of Zj and Zj plus 1. Okay. Because you have taken at random Z1, Z2, etc. Okay. And in fact, the gradient of f will compute, in some sense, the obstruction of this broken trajectory to be a true trajectory of the dynamics. So those vectors here, so those vectors in CD plus 1 are in fact up to multiplication by I here are the partial derivatives of f sigma. So here you see that the gradient of f sigma is non-zero because this is a broken trajectory. So you see it looks a bit like the case of geodesics if you already study this. So, and when you have a true trajectory of the dynamics, the gradient is 0. So in symbols, it is well, this relationship. And so critical points of f are in bijection with fixed point of capital phi. And well, well, the bijection is simply given by the projection on the first coordinate, as it is the case when you study intersection of Lagrangian and of a Lagrangian generated by a generating function with variable q sigma, and you are looking for, well, the intersection are given by the projection on the main variables in the critical set. Okay, so this discussion is true, for instance, when can be done for every Hamiltonian which is compactly supported. In this case, there are finite decomposition. And for us, if you look at C-equivariant Hamiltonian diffeomorphism, it works the same. The C1 clause, it means the restriction to the sphere is of sigma j is C1 close to identity, of course, because at infinity it's proper. Okay, and in the case where capital phi is C equivariant, so when it satisfies this equality, you can build a generating function that satisfies this complex two homogeneity as was satisfied by the Hamiltonian map. Okay, and thus C lines of fixed points of capital phi are in bijection with C lines of critical points of F sigma. And because of this relation, the Euler identity implies that they have critical value 0. Okay, but here we have C lines of critical points. So it will be easier for us to work with fixed points. So we will take the projectivization of F, meaning we will take, well, what I call here F hat, which is the quotient map once you have restricted F to the sphere. So that this diagram commutes, for instance. So critical lines, C lines of critical points of F now gives us one for each C line, one critical point of F hat. And these critical points must have critical value 0 because it originally have. And in fact, this is a bijection once you've said that you are looking at critical points of F hat with critical value 0. In general, a function on a compact manifold, the closed manifold CPN, will have other critical points, maximum and minimum, will certainly not have the value 0, quite certainly. And so that's all the other critical value have no geometric information for us, no geometric meaning. It can, it has to do with Lagrange multipliers of F restricted to the sphere. But it's not, it will not give us an insight. Okay, so let me recap what is our variational theory like here. So, and this is mainly the work of Givental and Théret here. So we are, first, we were looking at fixed point of a small phi, our Hamiltonian of CPD, Hamiltonian diffeomorphism of CPD, with action value T. We've seen that this corresponds to C lines. This fixed points correspond to C lines of fixed points of exponential minus 2ipt with the same t there, capital phi, our lifted Hamiltonian map, Hamiltonian diffeomorphism. And so, with what we've seen just before, those are this, those corresponds to critical points of ft hat for some Cp big N with critical value 0. And here ft is a family or C0 family of generating function of exponential minus 2ipt capital phi. Okay. Okay, so in order for us to have an interesting so we have an interesting variational principle, and now we want to apply Morse theory in order to study fixed points of small phi. And so this gives us our elementary analog to Floer homology of phi. So, as I've just said before, we can build a family of generating function ft with the explicit formulas. It's easy to see that we can do this. We can build a family of generating function as long as we fixed a compact interval, AB here. So we have this family ft of generating function associated to exponential minus 2ipt capital phi with the explicit formulas and the fact, well, we can compute explicitly the generating function of the rotation exponential minus 2ipt. We see on the formulas that f is decreasing with t. And so the sublevel sets, the 0 sublevel set, are increasing with t. And this is the case also for the 0 sublevel set of ft hat, as written there. And now, well, in the usual Morse theory, we have one function with a lot of and we study all the sublevel set of the function, and change in topology of the sublevel sets implies critical points. Here we have a family of function, but only one sublevel set of interest, the 0 sublevel sets. So it will work the same way, and in fact, it's totally equivalent. In fact, there exists some function in some manifold, finite dimensional manifold, such that you can see that as the sublevel set S of the function, here T. And so a topology change at S equal T for the family of sublevel sets Fs hat, so the zero sublevel set of Fs hat will imply critical points, which, as we've seen just before with our variational principle, implies that there exist fixed points with action T.
Can I ask a question?
Yes.
So first of all, this restriction to a enclosed interval from A to B, this is because you need to keep subdividing, and if you have more and more rotation, you need more and more dimensions in order to achieve this.
Yes, this is exactly that.
And this thing that you just said about there exists a function from M to R, is this M just maybe like CPN cross the interval?
Yes. Well, it's a hypersurface of that. Yes.
Okay, thank you. I just wanted to know whether this was some abstract theorem or something kind of concrete. But you're saying you can just write a formula.
This is totally concrete. This is it's only taking T such that Ft hat is less than is equal 0.
Thank you.
Yes, and yes, something which can look strange is that F, because of the decreasing here, F1 is in fact always different from F0, but they both are generating function of the same Hamiltonian diffeomorphism. But as was just pointed out, when we are constructing this family of Ft, we are continuously changing our subdivision of small Hamiltonian diffeomorphism, and so the best point of view is to say that F0 is not only generating, well, it's not the generating function of phi, but of the homotopy phi t from 0 to 1. Whereas F1, because you take in fact you take you take this homotopy to decompose your phi 1, which is capital phi 1, which is capital phi, whereas F1 is associated to exponential minus 2ipt phi t. And so there will be differences between F1 and F0, and in fact, in some sense, up to stabilization, F1 is like F0 plus some Q, quadratic form Q, with the index of Q equal to 2D plus 1. Okay. Q is a non-degenerate quadratic form. Okay, so maybe I will go a bit further with that just after this. So the most theoretical analog to the Floer homology in the action window AB of phi will be this group GAB of phi, which is up to a shift which is linked to the size of the decomposition of capital phi of these sublevel sets. Okay, so, and this you can as I see just before, you can see it as the homology, the homology, the Floer homology in the action of a function f in the window of value AB, the usual Morse homology, well, which coincides with the usual object in Morse theory. Okay, so in fact, it will share. Maybe well, it might be isomorphic to the Floer homology. In fact, it will share every important properties of the Floer homology, and that is why we can retrieve all the theorem I have introduced in the beginning of the talk, using this this analog. And for instance, what I've written there, that F1 is up to stabilization F0 plus a quadratic form with the index 2D plus 1. This will be linked with the following periodicity property, that if you translate the action window by 1, you will get up to a shift in degree, a shift by 2D plus 1, the homology in the in the action window AB. Okay. Okay, so this is well, like in Floer homology. In Floer homology, this would be the Q. This would be the Q operator, and here the map which goes here from there will okay, sorry, which goes from here from there, from here to there, is essentially, it will look essentially like the cap product with some class in homology, in cohomology, which is the class induced by the generator of the homology, the cohomology of of CPD. So CPN is equal to the U over U n plus 1. So there is a natural action of by the cap product of the homology of CPN. And in fact, this is this intersection here. And this must not be so surprising for those who know a bit about the quantum structure of the Floer homology on CPD, because the quantum operator works like works by counting intersection of a Floer trajectory, counting Floer trajectory that intersects some surface which has which will be, in the case of CPD, some complex projective space with dual, with Poincaré dual equal to UD plus 1. So this is not surprising, in fact. hopefully. So in order to state a bit more the properties of the homology in this the homology of phi in an action window, I will give you its an instance of its barcode. So a barcode for me is just a way to represent how the homology evolves with t increasing. So just as an example of what a barcode is, take the height function of this sphere, which is the projection of this sphere on the interval there. Okay, so x is there, if here f of x. Okay, so this is a way to see how the dimension of H star evolved. So here, say we are on some field F, over some field F. So in the beginning, until this value, there are nothing. The homology of the void is 0, nothing is to be put. Then we have the appearing of one homology class, the homology class of the, in fact, will of the H0 f of S2, the homology class of the components, of the connected component. So in fact, it will give us H0 of S2. Okay. At the second critical value, there is a new class of degree 0, because the sublevel set is divided into two connected components, and it will disappear with the third critical point, because it will it will join. It would be joined with the first one, and finally there is a last homology class of degree 1, H1, which generate S1, H1 of S2. Okay, so this was just a very basic example in order to be sure about what is a barcode for me. So now we do the same, but with G minus epsilon t, with t going with t increasing. So there will be some as both these classes, there will be some class that are necessary there. So here I take CP1 as an example. So there will be infinite bars which will correspond to class generated by CP by some projective subspace CPK, then CPK plus 1, which can be seen inside H star of CPN with n very big, very large. Because of the periodicity that I've talked about just before, we will see them we will see associated infinite bars, one integer after that, and one after, etc., etc. Okay. And as I said before, if you are looking at some time there, the class here, alpha, and here it can be formulated precisely. It is related with this class there by taking the cap product by ud plus 1, and here ud plus 1 is u2. If you take u1, you go there. Okay, and you can have also, you could have other class, other bars, but all of the other bars are finite bars because they are not associated with the homology of CPN. And so, yes, this value, the ending points of the infinite bars are the spectral invariants. And so the fact that they always exist proves the Fortune-Weinstein theorem. It proved that in our case, we have at least two d plus 1 equal 2 fixed points. Okay, so I will not prove the theorems above, of course. Don't have time for that, but maybe I can take just 1 or 2 minutes to say that one very interesting thing in the interesting property in the proof of the theorem of Shelukhin. Well, in fact, the theorem of Shelukhin is the consequence of two remarks, of two independent facts, two independent theorems. The first one is that, if I denote by beta 1 the length of the first family of small of infinite bars, say there is another family of finite bars, all the same because of them same length because of the periodicity theorem. Well, the first remark, the first theorem is that for all j, beta j is less than 1. In fact, strictly less than 1. And the second one is that if you denote beta total of phi over some field f, the sum of the beta j for the families, for each families of bars, you have that beta total of phi p over the field phi p, fp, of the field with p elements, is more than beta total p times beta total of f. Well, and the theorem is very simple once you have both of this remark because if you have more than d+1 fixed points that are visible in the level of homology, then you must have beta total more, which is strictly more than 0, non-zero. And because, well, if you had finitely many fixed points, you should have a bounded beta total because of this, bounded with the powers of P here. But you have also this, this relation. So it cannot be bounded. So this is for all prime. Okay. And in fact, well, yeah, I will stop there, but this inequality is not so hard to prove in with generating function. The first one is a bit harder for in the point of view of generating function, but this one is a very simple consequence, simple, although tricky consequence of a classical Smith inequality. Okay, I will stop there. Thank you very much for listening.
Thank you. So are there any questions? Well, I have a question. So I can imagine this Smith inequality that you're using in this second part. Can you say something about this, the fact that the bars don't have length greater than 1?
Well, the proof is not very original because this is the same. This is in fact the same as the proof of Igor Shelukhin. So it's the well, the general thing underlined by that is that the distance between barcodes of phi and the barcodes of psi. Once you know what is the good distance for this, so the bottleneck distance is less than, well, I think this is 1/2, but well, it's not really important, of gamma of phi psi minus 1. So this gamma can be defined in this case also. So, and well, so this is defined with the help of spectral invariance. This is a C d+1 phi minus C1 of, for instance. Well, you can take K there and take the infimum if you want. And the way to prove it, and this is well, this is the maybe well, the famous trick in persistence homology is to find an interleaving between the between the persistence module of phi and the persistence module of psi. That is, if you have well, the homology of at time t of phi, then the homology time t plus say delta. Well, you have more. You have the inclusion morphism there. Here, well, I will do the case with the identity. you have to find a map, interleaving maps, which are morphism, which are compatible, which commute with the persistent module, and which have this strange things that if you do this one, then this one, you commute with the inclusion morphism. And this is in the proof of Egor. This is done with a pair of pants products, and in the case of generating function, this means that you must have some way of taking the product of a class of phi and a class of the homology, the homology of phi minus 1. And this is, well, this is a bit tricky. It's a bit technical. I cannot do into details, but there is way to define some kind of product. Some kind of product of the form T phi G T plus S, something like that. And this can be done using explicit formulas with composition of generating function, taking the generating function of phi, of capital phi, of capital psi. Mm-hmm. Well, there is a map. Well, I cannot do much more details here, I think.
Well, thanks. That was helpful. Any other questions?
I had a question. At the end of your notes, below what you're showing on the screen here, you had a bit more written. I was wondering if you said something about that and I missed it, or if you could say something more about it.
No, I didn't talk about yes. So there is a so this is about the second point. So here I have talked just a bit about the first point, but it's a bit technical. But the second point in the proof of Egor, so this inequality in this Smith-like inequality for the beta total, so the sum of the lengths. I can explain very quickly how it can be proved with generating function. It is a consequence of the classical Smith inequality, which is that if you have the group Z over PZ, so the cyclic group of the P, which acting on the topological pair or space of finite dimension, you have this inequality. So, well, this is a very standard result of transformation theory. But once you have that, you can derive almost automatically inequality on the generating function homology of a Hamiltonian diffeomorphism. You can do this for compactly supported Hamiltonian, and you can do this in our setting for CPD, just because the generating function I did not give the formula of F, but if you take iteration of capital phi and you take the decomposition associated with it, the new generating function will be a generating function with p times more variables as in the initial case, because there is z1, etc., zn. So this what I call z bar there, and then you have you have all the other iterates corresponding to the other iterates of capital phi. And there are symmetries because this is the same phi p times. In fact, the function, it reflects on the generating function in the fact that it is there is a cyclic symmetry here. If you do a cyclic permutation of the variables, you get the same values, and it's directly linked to the first generating function if you took the p time the same tuple of z. You get in fact p times the value, the original, the value for one tuple taken by f. So once you know all of that, you apply the Smith inequality with the sublevel set of your function. So in the case of Hamiltonian with compact support, you'd use this kind of sublevel sets, and you get the usual, well, something which is already known and was proved by Shelukhin also, and by Seidel in the case p equal 2, which is this, which is true for aspherical manifold and for us in CD+1 because we use generating function. And in CPD, it's a bit trickier. It's not as direct, but you get this inequality. And essentially by integrating this inequality, you get beta total. Well, it's not, well, it takes, well, it's a very simple procedure, but it's a bit tricky. It was also found out by Egor. But this way, you have a very quick proof of this fundamental result, fundamental in the proof of the theorem of Egor.
Thanks.
Maybe at this stage we end the question session. Maybe we should thank Simon one more time. So let's do that.